have the set of games that have exact potential function, and in fact, I didn't say that, but now I am saying this set is equivalent to congestion games. So not just that congestion games all have the exact potential function, also the other way around is true. If you have a game that has an exact potential function, there is a way to represent it as a congestion game with resources, sharing resources, and so on. Okay, so these are two isomorphic sets. Then, by definition, every exact potential is also an ordinal potential function, right? So this set is contained in the set of ordinal potential games. And also, by definition, every ordinal potential function is a generalized ordinal potential function. Satisfies the condition, right? So this is contained in the set of generalized. Then we said that all those games do possess a Fusraj-Nash equilibrium. But there are also other games that do have a Fusraj-Nash equilibrium but do not have these functions. So the set of games where there is a Fusraj-Nash equilibrium is actually larger than this set, but it does contain all those games. And then when outside you have no Fusraj-Nash equilibrium. So, and the inclusion here is strict. So there are games in every class here. So there are games where there is an ordinal potential but no exact potential. There are games where there is a generalized potential but no ordinal potential. And there are games where there is a Fusraj-Nash equilibrium but no any type of a potential function. So congestion games belong here, so they have an exact potential. That's a very strong condition, and that's very nice. Then they have that. What is not nice about them is, even though they do describe many real-life situations, there are some assumptions made in the model that do not fit everywhere. First of them is the utility. The structure of the utility function is quite constrained. That's a linear sum of utilities of the resources you use. But not always you are interested, in the sum of utilities or costs you have from the resources. Sometimes you just want to, you're interested. You use several machines, but you're interested only in the fastest one that you use. Right? So you would need a maximum or a minimum instead of the sum. So the utility function is constrained. Then we also assume that the resources are independent. The utility or cost function per resource does not depend on the same function on other resources, so there is independence between the resources. And also they are reliable. As long as you use it, you will get what you get, described by the function of utility or cost. So they don't fail. The players are homogeneous. The cost to utility to each user of a given resource is the same, given by the function of congestion. And there is a synchrony in the sense that those utility or cost functions depend on the total congestion of the resource, but does not depend on actual order by which the players use the resources. You can imagine that the resources are machines, and not all the tasks are actually executed in parallel. Maybe they're executed one after another, so the completion time is not quite the same to all the resources of that machine. Right? It depends on the order in which those tasks use the machine. So in the congestion game model, this is not taken into account. So how can we modify the model so that we can take into account those things? And there were a few works that tried to do that. The first one was to allow for player-specific utilities for the players, so that different players would enjoy the resources in different ways. Okay, that would be the case. Some want to get from A to B faster. Some prefer an empty train. You know, so from the same congestion, you may have different utility. Another model is weighted congestion games. I'll give you an example later, probably, maybe in homework. In weighted congestion games, you have agents that have different weight on resources. So here we only counted the congestion of the resource was given by the sum of users. Here every users may have different weight. Okay, if I join the resource, I bring congestion 1. Someone else will bring congestion of 3. Okay, because they are more important. So different agents may have different congestion. And it's not quite the same as to, so some would say that you may decompose a big agent into, you know, a few copies of himself, but that does not always work because all those copies must go all together. Okay, so that does define a different model. Then there are splittable congestion games. They describe situations where you have a given package, actually bulk of packages that you have to send, and you distribute those in the network. Okay, so you have some amount that you have to send through the network, and you just split this amount in the network. Local effect games describe situations where resources are not quite independent. So if you have neighboring resources, then the utility functions on them depend on each other. Okay? Which makes sense in the situations where, if there are roads in the network, then if you have congestion on one road, then probably there is more congestion on the neighboring roads as well. Congestion games with failures account for possible failures that you submit a task to a machine, the machine just fails and does not execute the task. Random order congestion games account for different ordering of the tasks on a given machine. And the congestion averse games, that's a general model that covers quite a few of those, and that's the one that we're going to talk about now. As before, say, that's a more general setting than just congestion games. I just call it a congestion setting so far. It's not a game yet, but we'll make it a game. So we have, as before, the set of players. We have the set of resources that they're going to share. As before, the strategy to players to choose a subset of resources, and we have, for each combination of strategies, we have the congestion vector that indicates how many users we have on each resource. That's all as before. Now, when I have a congestion vector, I can look at a particular player, and for him, I can construct what is called the personalized vector of congestion. Is the same vector of congestion that would have the same congestion on the resources that our agent uses, and it will be 0 on the others. Why? Because I don't care about the resources I don't want to use. Okay, so from every congestion vector, we can look at it from the perspective of the given agent and look only at those entries where which I have chosen, and zeros on the others. And then for any given vector of congestion, whether personalized or not, just a vector of congestion, we can we will call the support of the vector all those entries, the indices of the resources where we have non-zero congestion. Okay? So if I look at resources that I use, that defines support of my personalized congestion vector. Right? And now assume that instead of defining the utility per resource and taking the linear sum of those utilities for each agent, we just take the personalized congestion vector of each agent, the whole vector, and there is some utility function that translates that personalized congestion vector into real value in some whatever way that we denote. So that's a very general model, and of course we cannot expect good behavior from that model, so we would have to make some assumptions to conclude some positive properties. But in this way, it would be possible to model non-identical resources that are mutually dependent, as in local effect games, resources that may fail or have different orderings of tasks submitted to them, because the form of the function can be pretty much anything now. We may have players with different interests. So pay attention here that the utility function is player specific. It has index I. So this function may have different forms for different agents. One agent would like to minimize his cost, another agent wants to maximize the probability of success, the third agent would like to do anything else. So they even may have completely different interests in the game, not just different parameters for a similar function. And we may have, very general utilities indeed, very general utility functions. So, as I said, it would be difficult to expect good behavior from such a general function, so we will make assumptions, but hopefully still realistic assumption. The first one is monotonicity. The name is congestion averse, meaning that congestion has a negative impact. Similarly, it could be done for the opposite case where the agents like congestion. Okay. Mathematically, exactly the same, just another, what we need actually is monotonicity, one or the other way around. Let's fix this particular way. Okay, so the utility function are decreasing when decrease when the congestion increases. The second condition is submodularity. Do we know what submodular functions are? The simple special case is concave functions. The higher the function is, the slower the growth. Okay. So that's concavity when we have a real valued function. Here, the condition of submodularity is not precisely as in functions. It has its particular context, but the idea is the better your strategy is, the less is your incentive to add resources. The higher you are, the slower you grow. But here in the sense of the better collection of resources you have in use already, the less is your incentive to add one more resource to what you have. We will define it formally, but that's pretty much the idea. And the third assumption is independence of irrelevant alternatives. What does that mean? If I have two resources, and I prefer resource A over B at a given congestion on them, then it doesn't matter what happens on other resources in terms of congestion, how many resources I or other agents use, what's going on over there. my preference between these A and B at the same level of congestion on them only is the same. Okay, so my preference between two resources at a given level of congestion does not depend on irrelevant alternatives, does not depend on what's going on around. To define that formally, we need to make some definitions of moves, simple moves, and, well, elementary changes. Those are moves with single resources. There are three types of them: add a resource, drop a resource, switch a resource. Just a single resource. Okay? So I would call AIR the add of resource R by agent I. Okay? So he adds resource R to his strategy SI. Drop, DIR, agent I drops the resource R. So resource R goes away from his strategy, and switch from resource R minus to resource R plus by agent I is just moving from one resource that agent I had in his strategy to another one that he hadn't in his strategy. And this can be decomposed into two operations: an add of resource R plus and the drop of resource R minus. So these are three elementary changes that an agent can make. And with the help of those changes, we can define the three conditions that we have on the utility function: the monotonicity, independence of irrelevant alternatives, and the submodularity. So monotonicity is very simple. Note that monotonicity only applies to two congestion vectors with the same support, with the same non-zero entries. Okay. And then we say that the higher congestion we have on a vector, so we have congestion vector H and H prime, so that on each resource the congestion in H is greater than the congestion in H prime, but these two vectors have the same support, have the same non-zero entries. If this is not, if the support is different, we don't require anything. So monotonicity only applies to vectors with the same support, and then the higher congestion you have, the lower the utility of using that, of having the same that congestion vector. That's monotonicity. Independence of relevant alternatives. We said if we have two resources with the given level of congestion, our preference should not be affected by what's going on otherwise, elsewhere. So if the switch for a given agent I from R minus to R plus is profitable from the strategy profile S, okay, then it should be also profitable for agent I from any other possible profile S prime where, as before, our agent does use R minus and does not use R plus, so that it would be possible actually to switch from R minus to R plus. And also the congestion on these two resources only is exactly the same in S and S prime. What's going on elsewhere does not affect the choice of agent I. Okay. Let's look at the example. So for monotonicity, we look at two congestion vectors, 307, 305. What's important, the two vectors have the same support, 1 and 3, and there is a 0 in the same place. And then we see that the first congestion vector is higher than the second one, so the utility from 307 is lower, than the utility from 305. Now for independence of relevant alternatives, we consider two situations. So here we compare the utilities from using resources 1, 3, and 4, or 1, 2, and 4. Okay, so there is a switch from third resource under congestion 5 to the second resource under congestion 7. And our agent does prefer that to this. Now I make changes elsewhere on other resources. Okay, now our agent does not use at all the fourth resource. The congestion on the first resource is different, higher than before, but still the choice is between the third resource in under congestion 5 and the second resource under congestion 7. And still the preference is exactly the same. Okay. And submodularity, the third condition. So we said the better strategy we have, the less is our incentive to add resources. What do we mean by the better? The better in terms of if we could make profitable switches, we would have made them. Okay, so the quality of the resources that I use is greater than the quality of the resources that I do not use. I cannot, the set of resources is big enough, so if comparing two sets where one is contained in the other, the larger one is better. I have more resources to use. Okay. And if I compare two strategies where I use the same set of resources, but one is less congestion, another one is more congestion, of course less congestion is greater. So that means that, so here we would compare, it looks a bit ugly, but it's not hard to read. We compare adding one more resource, either to congestion vector H prime, or to congestion vector H, how do you say that, 2 primes? What's the right way? English speakers have double prime. So we compare adding a resource to H prime or H double prime. Okay? So, and adding a resource is just to add in a congestion vector whose support is of size 1, which means there's exactly one resource where we have positive congestion. Okay, so that resource we would add to either H prime or double prime. So if we have H prime and H double prime, and we compare their supports, and their supports are different by exactly one resource on each side. That means that there was a switch in between H prime and H double prime. Right? And if that switch was so that we prefer H prime to H double prime, then adding a resource to a better congestion vector, which is H prime, should be less than adding it to H double prime. Okay. So in H prime and H double prime, we use some resources with the same congestion, and there is one resource here and one resource here. Let's call it A and let's call this B, making the switch from B to A is profitable. So having this strategy is better than having that strategy. And then adding one more resource here is less profitable than adding one more resource. Now if we have H double prime, the support of H double prime contained in support of H prime, that means that here I use same resources as here but more, some others as well. Okay, the congestion on each resource here is the same. Then also adding a resource to a larger strategy has less impact than adding a resource to a smaller strategy. And finally, if we have two vectors with the same support but one is just less congested than the other, then also adding to a less congested one has less input than to a more congested. Okay, so that's submodularity. Intuitively, once again, the better strategy you have, the less is your incentive to add. Those are particular examples for these three strategies. So in the first case, we compare between adding resource 2, right? So we know that we prefer using resource 2 under congestion 3 to using resource to using the first resource under congestion 5. Okay. And now we add, I made a mistake, sorry. Now we add the third resource with congestion 1. Okay. So adding it to the better strategy is less profitable than adding it to the worse strategy. Here we have more resources in use already than in there. Okay, here we use the third resource, there we do not use the third resource, and we add the second resource, so there's less input here than there. And here we use the first resource in both strategies, but here the congestion is 5, there the congestion is 7, so adding to the less congested one has less input than adding to the more congested one. And now we say that a game that has the utility function that has those 3 properties would be a congestion averse game under one or more condition, not on the utility function, but on the strategy sets. Let me explain that indeed. Matroids, I would guess you don't know what's that. Okay. That's a big theory of them, but the only thing that you need is the definition. And it's actually written in the footnote. The matroid is some subset of a power set of a given set. Okay, so if we have some set X, you look at its power set, so all the subsets of X. Matroid would be some subcollection of that. Right? But it is a subcollection that has particular properties. And the properties are if you have some subset of X in our matroid and X is there, then all its subsets also must be there, so it's closed. So matroid is a closed collection. And also if you have two sets V and Y in the matroid, so that Y is strictly larger than V, then you can always find an element over there that you can add to V, and the result will be in the matroid again. Okay. So this is a subcollection of the power set with these properties. Why these properties are important to us is that because of this, let's say, in a way, continuous structure of the matroid, we can move from element to the element in the matroid. Elements of matroid are subsets, right? There are sets of elements. By making small changes. This is what we need. And now, why matroid structure is important, is actually relevant to us, is that we can model the strategy spaces of the agents as matroids. Okay? You remember that the strategy space of an agent is what? Some subcollection of the power set, right? Some collection of subsets of the resources that we have. So for each agent, his strategy space would be given by some matroid Mi that would satisfy those properties. And also two integers just to bounce on the sizes of sets in the matroid, in the strategy that we can use, so that the space would consist of all the subsets in the matroid whose size is in between these two bounds. Okay, so for each agent there is a matroid and two numbers. Then take all the sets in the matroids, throw away all those which are smaller or larger than these bounds. That's it. What is left is the strategy space of the agent. Okay, know that if you take ni and mi the same number, then that means that we will use these sets of the same size always. If we take 0 and whatever infinity, then you will use the whole matroid and so on. So that's quite flexible structure there, but it does have this property which allows us to make small moves in between these strategies. And that's what we want to have. Questions so far? So now let me just, so that was the model. We will just see now that there are many games that we mentioned before that actually fall into this model. So there was the first line that I mentioned, games with player-specific strategies. In that model, there was a limiting condition that the strategies that the agents use are singletons, and the utilities are decreasing. Now, decreasing utility set monotonicity holds. Okay? Singleton strategies gives us independence of relevant alternatives, because that thing that doesn't matter what happens around just does not exist. We always compare between two single sets. Submodularity as well. It will just, you compare in a switch all the time, just a single switch. So it is congestion averse utility, and singleton strategies are actually, there are parts of matroid with Ni and Mi both being one for every agent. Okay, so that is also satisfied. That is a special case of the model. Another model was congestion games with load-dependent failures. So the resources may fail. So in that setting, each player would have a task, and a task can be carried out by any of the resources. Now, each resource may fail to execute its assigned task with the probability that depends on the congestion on the resource. Okay. And now, what an agent would do, given possible failures, you probably would assign your tasks to more resources than you actually need. You need one, but you might assign your task to a few, hoping that at least one of them will execute the task. Right? So you would say that task execution succeeds if there is at least one resource to which you submitted and it did not fail. Okay. Now, what an agent, so if there is no cost to pay for use the resources, then of course you would submit just to all of them. Right? So there is a cost to pay. And the utility to a player would be then just the difference between, so there is some reward that you get if your task is executed, VI, and you get that reward if your task is successfully executed. So that's the probability of that. So that's 1 minus the joint probability of all the resources that you used to fail. Right? So that's a product over all the resources in your strategy, failure probability function that depends on the congestion, minus sum of costs for all the resources that you use. Okay. Now, first of all, yes, it is realistic that the failure function depends on the congestion, but also if failure probabilities were constant, okay, not congestion dependent, then all this part would not depend on the strategies of other agents, right? This is a constant thing, this is a given parameter, it does not depend on what the others do. The only thing that does depend on what the others do is those costs, which are congestion dependent. But this is exactly the cost function in the original congestion game model. Just a linear sum of some function of congestion over all the resources in use, right? And about those games, we know that those games are really nice because they have a potential function. Now you have something with a potential function plus a constant, it would have a potential function as well. Okay, so considering constant probabilities of failure, not just less realistic, but also not interesting in terms of theory, we know everything about them already. Okay. Those games do not have a potential function, but they do fall into the framework of our congestion-averse games. Why is that? This function would be monotonically decreasing with congestion, given that costs increase with congestion and the failure probabilities increase with congestion, of course. It will be independent on irrelevant alternatives and submodular as well. And here it is assumed that the agents may use all possible subsets of the resources, so the whole power set that satisfies the Detroit condition. So that's one more special case. Another one, random order congestion games. This is a model where you do count on the particular order in which you execute the tasks on a given machine. So once again, an agent has a task that can be carried out by any of the resources, and each resource executes its task in some random order. Okay, so why this order is random? There are two explanations to that, two possible applications of that. One is if you send the task over a network, then the delays may be random, and then they arrive at random time, or you have tasks physically submitted, and the machine just randomly chooses from the pool that it has. Then, again, given that your task may be first or last at each machine, you might want to submit your tasks to several machines so that you would increase the chance to make it faster. Okay, at least one of them. And of course, if there is no cost for using the resources, then you would submit to all of them, so there is a cost. Your total cost in this model is the sum of costs. There is a fixed cost for use of each resource, and this is how many resources you use here. And this is the cost of completing your task at the fastest machine. Why is that? Say a bit of basics of probability theory. So that's the expectation. That's the expectation of. So that cost would be just your ordering number on a given machine. So that's the expectation of your ordering number on the fastest machine. What's the expectation? If we have a random variable, you remember that a discrete random variable, you go over all possible values, right? We look at the fastest machine. So your order on the fastest machine would go from 1 to what? The minimum congestion, the fastest machine that you have. So in all your resources, you take the one where congestion is minimal, that would be the fastest machine. Well, at least the value of where you are the fastest will not be longer than that. And now the expectation is take the value, multiply by the probability of getting that value, right? But there is an alternative formula of expectation, which is called the tail formula. I don't know if you know this. Instead of taking this and multiplying by the probability having that value, remove that. And replace that. That will give you exactly the same value. And that's the probability that we have over there. Say, having the value greater than that. So if the minimal is greater than that, that all of them are greater than that. So that's the value which is above Q divided by the whole amount. Okay, given uniform distribution. Okay, so that's just the probability that your ordinary number is greater than Q, greater or equal than Q. And once again, all the conditions of congestion averseness hold here, and every agent is allowed to use any subset of the resources, so the Matroid condition also holds, and that is a special case of the model. So what do we know about those games? So they do capture quite a few applications indeed. The model is general. Can we say anything good? Well, not about everything. For instance, the finite improvement property will not hold anymore. So there is no even generalized ordinal potential function, and of course no exact potential function, and so on. So no potential function in these games. But there is still a Nash equilibrium in pure strategies. And in fact, there's more than that. Not just it exists, it can be found in polynomial time. So we can show a polynomial time procedure that will lead to Nash equilibrium, in fact, from every possible strategy profile, which means that those games are, if you quote the term, weakly acyclic. Okay, say any better response dynamics or best response dynamic may cycle and not lead to an equilibrium, but there is some path that does lead to an equilibrium, and more than that in polynomial time. Okay, that's good. And there is one more result saying that you actually can't do any better. If you relax any of the conditions, any of the assumptions that we made, then two things. And that equilibrium is not guaranteed to exist. And it's actually MV hard to determine whether it exists or not. Okay. Is everyone in the group knows what MV hard is? Good. Okay. In 7 minutes, let me show you some things. Well, this is a proof that there is no ordinal potential in this game. We have 4 resources and 2 players, and I do not consider all possible profiles. All possible profiles, and consider only 4 combinations where I will show that that's impossible to construct an ordinal potential function. So the payoffs would be 1, 1, 3, and so on. So here the potential function must drop, there it must drop, there it must drop, there it must drop again. So there is a cycle, okay, a strict cycle, and we can't find numbers that would satisfy that. So that's impossible to construct a function. it leads us to the fact that this number must be strictly less than this number. Okay. But there is a polynomial time computable Nash equilibrium. How do we show that? I'm just wondering if I have enough time. I think I can. I know you're tired. The idea is very simple, and it uses all the properties, and particularly the Matroid property, strongly. So instead of considering on all possible deviations, say what do we have at hand? The strategies for the players are subsets of resources, so there are exponentially many in general, right? All possible subsets of resources. But since we have this Matroid property, we can move from one strategy to another with small steps. And in fact, here it will realize in a very strong property saying that if an agent has a deviation, any possible deviation, then there must be a deviation which is an elementary change. A drop, an add, or a switch of a single resource. What does that mean? Instead of checking all possible deviations, it's enough to check only these elementary changes. There are polynomial time to check those, okay? Because there are just changes of a single resource. And we can construct a dynamics that uses just two types of not two types of moves, but two types of sequences of moves. We call them a drop and a swap ladder. And they will be following way. A drop ladder would be a sequence of consecutive moves, well, all of them profitable moves for the agents that make them. The first agent makes a drop, so the congestion on one of the resources drops by 1, and then someone else switches to that resource so that the congestion on that resource is back to the same as it was before. Congestion on another resource is less than drops by 1, someone else switches there, and so there is a sequence of some m profitable switches. As a result, the congestion on only one of the resources is dropped by 1, the last one in the sequence. And a swap ladder is a drop ladder that is followed by an add on that last resource. So such a sequence of moves actually preserves the congestion on the resources. Okay. And then we can show that having applied only those sequences of moves, we will get a Nash equilibrium. Why is that? I'm not going to prove everything. I'll just give you the milestones in the proof. So we can talk about resistance or stability of a profile against adds, switches, and drops. Okay, the elementary changes that we have. And we said that in this case we have this beautiful property that if the profile is stable against adds, drops, and switches, it is stable. Right? So we only need to check these three types of stability. So the first thing to show is if we restrict ourselves to the profiles where every agent uses maximal number of resources he has, we can always get there. Let all of them just add resources as much as they can from every profile. We get there. Then, if we have, then we can reach from every profile where everyone uses maximal number of resources. We, in polynomial time, can reach a profile which is stable against adds and switches. Okay, so we can guarantee 2 of these 3. Now we need to take care of the last one. Okay? Now, if we have something which is stable against adds and switches, then we show that applying a swap ladder does not ruin that property. Good thing. Okay. Second thing, there cannot be more than polynomial time of swap ladders. Okay. So we can take our agents to a profile where they use maximal number of resources, do whatever the previous procedure wants to reach in polynomial time, adds and switch stability, then apply all possible swap ladders that they may have. There will be only polynomial time of them, and we will not ruin stability against adds and switches. Now, the only thing that we may need to deal with is if someone has a profitable drop. So there may be a drop ladder. Now, a drop increases the congestion on all the resources by 1. We have a finite gem. So they cannot be more than the number of resources and the congestion, the maximal congestion on each resource times where we can repeat the whole procedure. So we get there in time, which is polynomial in the number of agents and the number of resources. And I'll stop here, and yeah, how we know it's complete if we actually said that. If we change, if we relax any of the conditions, and Nash equilibrium may not exist, then it's going to be hard to establish whether it does or not. And we continue on those